Hello viewers, welcome to UGC EPG Pathshala. I am Dr. V. Venkatramanan from School of Interdisciplinary and Transdisciplinary Studies, Indira Gandhi National Open University, New Delhi. Today I am going to elaborate upon climate change and food security, which come under the paper Climatology. After studying this module, you should be able to define climate change and food security, explain the impacts of climate change on agriculture, discuss various dimensions of food security, explain the impacts of climate change on food security, and explain the importance of climate smart agriculture. We know that food systems, a product of human ingenuity, is a complex ecosystem whose outcome and sustainability is driven by its inherent potential and biophysical and social environment. Food security is the outcome of functioning food system and innate properties of the food systems. Food system and food security are influenced by a web of factors like climate change, technological interventions, and structural changes in the food system. Demographic changes, energy security, population pressure, and income-driven consumption pattern. The detailed study of climate change and food security help in better conceptualization of the effect of climate change on agriculture and consequently on food security. It is pertinent to know that the food security is dependent on food production, socio-economic condition, land use, trade policy, demographics, and food and waterborne diseases. It is hard fact to state that about 800 million people across the globe are food insecure, and about 2 billion thrive with food diet with insufficient nutrients. This grim scenario has led the global community to place utmost importance on food security, climate change, and kindred issues through sustainable development goals. As regards the relationship persisting among climate change, agriculture, and food security, there is an urgent need to develop climate smart agricultural practices, as today's humanity is facing greatest environmental challenge in the form of climate change and global warming. You would be well aware about the negative repercussions of climate change and variability on agrobiodiversity, soil resources, water resources, which eventually increases the vulnerability of agriculture. In this module, it is attempted to discuss the climate change and its impact on food security in the present-day society. Before we discuss the climate system, it is pertinent to know the difference between weather and climate. Although the words weather and climate sound similar, the difference exists between the terms from the perspective of space and time. We have studied that weather reflects the state of atmosphere at a particular time and place. Weather is a daily or short-term variation of different conditions of lower air in terms of temperature, pressure, wind, rainfall. On the other hand, climate is a statistical measure of state of atmosphere in terms of meteorological variables like temperature, rainfall, humidity, etc. for a particular region for a period of more than 35 years. The climate can fluctuate on short time scales, producing, for instance, the hydrological drought, and over much longer time scales, giving rise to glacial epochs. Having known about the difference between weather and climate, we will learn about the components of climate system. The United Nations Framework Convention on Climate Change defined the climate system as the totality of the atmosphere, hydrosphere, biosphere, and geosphere and their interactions. The climate system is powered by solar radiations. Since the Earth's surface temperature has been relatively constant for many centuries, the incoming solar shortwave radiation must be nearly in balance with outgoing long-wave radiation. About half of shortwave radiation is absorbed by the Earth's surface. About 30% of SWR is reflected back to space, and 20% of shortwave radiation is absorbed in the atmosphere. The long-wave radiation emitted from the Earth's surface is largely absorbed by the radiatively active gases like water vapor, carbon dioxide, methane, nitrous oxide, and other greenhouse gases. The downward directed component of this long wave radiation heats the lower atmosphere, and this process is popularly called the greenhouse effect. Another interesting concept with regard to climate change is climate forcing. We know that the climate system is a dynamic system in temporary balance. Changes in the climate system, either due to the natural or anthropogenic reasons, can perturb the Earth's radiation budget, resulting in a radiative forcing. that affects the climate. The forcings can be construed broadly as external and internal forcings. External forcing refers to a forcing agent outside the climate system, causing a change in the climate system. The galactic variations, orbital forcing and solar forcing are external forcings. On the other hand, the processes intrinsic to Earth and its atmosphere alter climate. These internal forcing factors include mountain building, distribution of land masses, volcanic activity, atmospheric composition, chemistry, and surface reflectivity. Now, let us try to understand the process of climate change. Climatic conditions are varying in nature all through the Earth's history. The weather records for most part of the world exist only for few hundred years in developed countries, but in less developed countries, the weather data exists for few decades only. However, the proxy indicators of past data from pollen analysis, tree rings, ice cores, beetles, and sediments have produced evidence for non-static nature of climate. The IPCC, in its 5th assessment report, stated that warming of the climate system is unequivocal. And since the 1950s, many of the observed changes are unprecedented over decades to millennia. The atmosphere and ocean are getting warmer with every passing year. The amounts of snow and ice are in decline. Sea level is on rise and the concentration of greenhouse gases is increasing. Climate change influences all the components of biosphere. Climate change can be defined as the variation in either mean state of the climate or in its variables, persisting for an extended period of time, typically decades or longer. It includes temperature increase, changes in precipitation pattern, sea level rise, and increased frequencies of extreme weather events. Further, climate change follows a specific pattern of change in climate or its variables over the time. On the other hand, climatic variability refers to sudden and discontinuous seasonal or monthly or periodical changes in climate or in its components, without showing any specific trend of temporal change. Global temperature is considered as a popular metric indicating the state of global climate. Global warming is defined as the increase in average temperature of Earth's near surface air and oceans due to transmission of incoming shortwave solar radiation and the absorption of outgoing long-wave terrestrial radiation. The globally averaged combined land and ocean surface temperature data as calculated by a linear trend show a warming of 0.85 degrees centigrade over the period 1880 to 2012. Between 1906 and 2005, the global climate system was absorbed by 0.74 degrees centigrade. Changes in many extreme weather and climate events have been absorbed since about 1950. Particularly, the number of cold days and nights has decreased and the number of warm days and nights has increased on the global scale. To contextualize the topic on climate change and food security, let us delve first on agriculture. Modern agriculture, with the aid of advanced technologies and practices like chemical fertilization, pest and disease control using diverse group of pesticides, irrigation, crop varieties and hybrids, etc., had increased global crop production substantially. However, converging trends in population growth, natural resource use, food prices, climate variability and climate change jeopardize agriculture production system, food and nutrition security, and agriculture sustainability. Systematic understanding of linkages between agriculture and climate change reveals the net negative impacts of climate change on crop distribution, crop production, emission of greenhouse gases from agriculture, and the potential of agriculture sector to augment the global efforts to address both adaptation and mitigation to climate change. Globally, croplands cover 1.53 billion hectares, while pastures cover another 3.38 billion hectares. Altogether, agriculture occupies about 38% of Earth's terrestrial surface, and it is essentially the largest use of land on the planet. Climate change will influence crop distribution and production and increase risks associated with agricultural farming. IPCC, through its various reports, categorically states that climate change affects crop production. In several regions of the world, and developing countries and island countries are highly vulnerable to negative impacts. Climate change induced extreme events such as drought, floods, marine transgression, abnormally high maximum temperature have become common occurrence in the last decade. As far as the contribution of agriculture to climate change is concerned, agriculture does contribute to climate change through greenhouse gas emissions. The changing concentration of greenhouse gases are key indicator of global climate change. Total anthropogenic GHG emissions from different economic sectors in 2010 amounts to 49 gigaton of carbon dioxide equivalent per year. Greenhouse gases emissions are converted into carbon dioxide equivalents based on 100-year global warming potential. This equivalent carbon dioxide emission is defined as the amount of carbon dioxide emission that would cause some same integrated radiative forcing over a given time horizon as an emitted amount of a greenhouse gas or a mixture of greenhouse gases. The emission data on agriculture, forestry and other land use includes land-based carbon dioxide emission from forest fires, peat fires and peat decay that approximate to net carbon dioxide flux from the subsectors of forestry and other land use. Agriculture sector accounts for about 10 to 12 gigaton of carbon dioxide equivalent per year. The greenhouse gases emission in agriculture are mainly due to land use changes and forestry, enteric fermentation, drained peat and peat fires, lowland rice cultivation and use of synthetic fertilizers and biomass burning as well. As regards the GHG emission from agriculture, the most cost-effective mitigation options are crop land management, grazing land management and restoration of organic soils. It is observed that policies governing agriculture practices are more effective when involving both mitigation and adaptation. With regard to impact of climate change, some of the direct impacts of climate change over the coming decades will be on agriculture food system. Climate change can affect agriculture through their direct and indirect effects on the crops, livestock, soils and pests. Climate change through its negative impact on crop yields increases the production and market risk and results in food insecurity among the vulnerable sections of the farming community. Climate change is reported to reduce crop yields. Globally, climate change is expected to reduce cereal production by 1% to 7% by the year 2060. Climate change could potentially interrupt progress towards a world without hunger. Climate variability and change will exacerbate food insecurity in areas currently vulnerable to hunger and undernutrition. Food access and utilization will be affected indirectly via collateral effects on household and individual incomes, and food utilization could be impaired by the loss of access to drinking water and damage to health. Particularly in the agriculture sector, climate change adaptation can go hand in hand with mitigation. Climate change mitigation and adaptation measures need to be integrated into the overall development approaches and agenda. Mitigation strategies to climate change is very important thing. Mitigation of climate change is considered as a human intervention to reduce the sources or enhance the sinks of greenhouse gases. Mitigation strategies essentially differ with crop and soil environment. For instance, the methane emission from lowland rice cultivation can be mitigated to a large extent through water and nutrient management, including mid-season aeration by short-term drainage, use of fermented manures, improved organic matter management. The nitrous oxide emission in crop land is reduced by adopting site-specific efficient nutrient management and also using nitrification inhibitors like neem oil, neem cake, nitropyrin, dicyanidamide, etc. As regards the methane emission from new ruminants like cow, sheep, etc., the emissions can be reduced by altering suitably the feed composition. The carbon dioxide emission from agriculture can be reduced by the adoption of conservation tillage practices, increasing carbon sequestration, improving soil environment, manure management and soil biodiversity conservation. Let us now discuss the adaptation strategies to climate change. Adaptation is said to be the process of adjustment to actual or expected climate and its effects. The adaptation strategies encompasses developing crop cultivars tolerant to abiotic stresses like heat stress and salinity stress, crop diversification, modifying and improving the crop management practices, harnessing the traditional or indigenous knowledge of farming community, adoption of conservation agriculture practices, resource conserving technologies, weather forecasting and agriculture insurance. To understand further the adaptation and mitigation strategies, we endeavor to learn the virtues of sustainable development. Sustainable development of humanity and our planet is challenged by a number of environmental challenges. The challenges are food security, water security, energy security, climate change abatement, biodiversity protection, and ecosystem service delivery. At the granular level, these challenges have commonality in terms of striking characteristics, occurrence, interrelationship, and these challenges demand concerted effort from United Nations and other organizations. The foremost challenge is food security, as it is related with other key challenges. The need to feed 10 billion people by 2050 with quality food and to provide clean environment demands productive soil, rich agrobiodiversity, augmentation of ecosystem services, continued energy supply and productive water use. The United Nations Rio Plus 20 summit in Brazil in 2012 committed the governments to create a set of sustainable development goals that would be integrated into the follow-up to the Millennium Development Goals after their 2015 deadline. There are 17 Sustainable Development Goals comprising 169 targets, and this global development agenda spans from 2015 to 2030. The Sustainable Development Goals, built on the successes of the Millennium Development Goals, are an universal call to action to end poverty, protect the planet, and ensure that all people enjoy peace and prosperity. The goals are interconnected. Often, the key to success on one will involve tackling issues more commonly associated with another. Unlike the MDGs, which are targeted at poor and emerging nations, this SDG will have a global reach. They will apply to developed and developing countries alike and will concern the earth system as well as people. The SDG framework addresses key systematic barriers to sustainable development, such as inequality, unsustainable consumption patterns, weak institutional capacity, and environmental degradation that the MDGs neglected. The SDG 2 aims to end hunger, achieve food security and improved nutrition, and promote sustainable agriculture. The SDG 13, it's a very important target, aims to take urgent action to combat climate change and its impacts. SDG 2 and its targets are intrinsically connected to almost all other goals. The food security is very well connected with soil security, water security, energy security, climate security, economic security, consumption pattern, gender equality, and political stability. Now, let us discuss about the relation between climate change and food security. The term food security initially was used to describe whether a country had access to enough food to meet dietary energy requirements. The concept of food security evolved, and the definition agreed upon at the World Food Summit in 1996 is that food security exists when all people at all times have physical and economic access to sufficient, safe and nutritious food to meet their dietary needs and food preferences for a healthy and active life. Primarily, there are four key dimensions of food security. The dimensions are availability, stability, access, and utilization. The first and foremost dimension relates to the availability of sufficient food, that is, to the overall ability of the agriculture system to meet the food demand. It is concerned with the production of food items for the population. The second dimension, stability, relates to individuals who could afford to have the food, the work availability, getting wage or salary, or self-production of food from their own land. It means the food has to be available to the people for the whole of the year. The third dimension, access, cover access by individuals to adequate resources to acquire appropriate foods for a nutritious diet. A key element in this dimension is the purchasing power of the consumers and the changes in their real income and food prices. It also referred to the movement of the people or the goods for proper distribution among the masses. Hence, transport is equally important to the food from deficient zone to the zone of deficiency apart from purchasing power. The fourth dimension, utilization, includes all food safety and quality aspects of nutrition. The available food has to be in a consumable state, and therefore the hygiene and cooking facilities are also of great concern. An important component of food security is nutritional security. In order to provide safe and nutritious food, the pulse crops, which are source of protein, should be included in the cropping system. The pulse crops, in addition to enriching soil fertility, enhance the livelihood security of marginal and small farmers. Nutri-cereals such as bajra, ragi, sorghum, maize, etc. are usually cultivated in rain-fed areas and are more climate resilient. Additionally, the demand for coarse cereals from nutritional point of view will act as an incentive for resource-poor rain-fed farmers to grow the climate resilient coarse cereals. Hence, in an era of climate change, climate resilient agriculture will play an important role in human nutrition security and livelihood security. Due to changes in consumption patterns, demand for fruits, vegetables, dairy, meat, poultry and fisheries has been increasing. There is need to increase crop diversification and improve allied activities. As regards the climate change impact on food security, we know that the agriculture crop production is a product of interaction between genetic potential and the crop environment. By adopting traditional and modern breeding methods, the plant breeders are in constant urge to increase the potential crop yield. Nevertheless, the farmers are not in a position to achieve the potential yield of crop plants. There exists a yield gap between actual yield and the potential yield. The yield gap is a function of biotic and abiotic stress in agro-ecosystem. The agricultural crop production will increase if the yield gap is narrowed down. Unfortunately, the yield gap is widening due to change in climate and consequent impact on the components of agro-ecosystems. Climate change will affect all the four dimensions of food security: food availability, food accessibility, food utilization and food systems stability. It will have an impact on human health, livelihood assets, food production and distribution channels, as well as changing purchasing power and market flows. Its impact will be both short-term, resulting from more frequent and more intense extreme weather events, and long-term, caused by changing temperatures and precipitation patterns, so on and so forth. People who are already vulnerable and food insecure are likely to be first affected very greatly. Agriculture-based livelihood systems that are already vulnerable to food insecurity face risk of increased crop failure, new patterns of pests and diseases, lack of appropriate seeds and planting materials, and loss of livestock. The need of the hour is climate resilient agriculture. At the same time, it is necessary to strengthen the resilience of the rural people and to help them cope with this additional threat to food security. In this context, agriculture research should be tailored to meet the requirements of climate resilient farming system. The way forward is extremely challenging for global agriculture, demanding a paradigm shift in agriculture crop production, agriculture development planning, investments in agriculture, and integrated farming approach empowering small and marginal farmers. It is important to transform and reorient agriculture production system by including resilient pathways to achieve increased agriculture productivity and at the same time capitalize the synergy existing between the mitigation and adaptation to climate change. It was timely that an approach christened as climate smart agriculture took shape in this century. With the proactive role of Food and Agriculture Organization and World Bank, climate smart agriculture aims at maximizing the global agriculture productivity, reducing the vulnerability of agriculture to climate change, increasing the resilience of agriculture system in the era of climate change, and reducing the greenhouse gases emission from agriculture. Climate smart agriculture is a comprehensive policy, technology and financing approach to enable countries to achieve sustainable agricultural development in the face of climate change. Climate smart agriculture includes sustainable agriculture and the need for adaptation and the potential for mitigation with associated technical, policy and financing implications. Climate smart agriculture includes farm-based sustainable agriculture, land management practices like conservation agriculture, crop residue management, agroforestry, manure management, etc. This climate smart agriculture is site specific and adopts ecosystem approach, integrated landscape management and ensure intersectoral coordination and cooperation. Climate smart agriculture approach strives to provide safe operating space for global food systems. To live sustainably within planetary constraints, we must grow more on the same amount of land using less water, energy and chemicals, and adopt sustainable agriculture practices. Climate smart agriculture can be defined as an agricultural approach that sustainably increases productivity, resilience, and reduces greenhouse gases and enhances achievement of national food security and development goals. The goals of climate smart agriculture are sustainably increase agriculture productivity and incomes in order to meet national food security and development goals, build resilience and capacity of agriculture and food system to adapt to climate change. The third one is to seek opportunities to mitigate emissions of greenhouse gases and increase carbon sequestration. Climate smart agriculture practices are adopted at all scales, including food supply chains and landscape. Climate smart agriculture addresses the challenge of meeting the growing demand for food, fiber and fuel despite the changing climate and fewer opportunities for agriculture expansion on additional lands. Further, climate smart agriculture emphasizes on poverty reduction and food security, maintaining and enhancing the productivity and resilience of natural and agriculture ecosystem functions. To summarize, it is pertinent to reiterate that agriculture has contributed immensely for the existence of humanity. Modern agriculture had exhibited its potential to feed 7 billion people. The issues and challenges related to agriculture gains urgency on account of growing human population, competing uses for natural resources, increased dependency on few food crops, lack of biological diversity in agroecosystems, inadequate knowledge of ecological processes and negative impacts of climate variability and climate change. Agriculture too contributes to climate change through the emission of greenhouse gases to the tune of 10 to 12% of global total greenhouse gases emission. Scientific understanding of the linkages between agriculture and climate change reveals the disruptive impacts of climate change on crop distribution and crop production and the potential of agriculture sector to augment the global efforts to address both adaptation and mitigation to climate change. In order to maximize the global agriculture productivity, to reduce the vulnerability of agriculture to climate change, to increase the resilience of agriculture system in the era of climate change, to reduce the greenhouse gases emission from agriculture, to achieve food and livelihood security, to reduce poverty and improve nutritional well-being of the people. International organizations like FAO, World Bank and Consultative Group on Integrated Agriculture Research conceptualized the reformative and transformative approach in agriculture called climate smart agriculture. Climate smart agriculture includes sustainable agriculture and the need for adaptation and the potential for mitigation with associated technical, policy and financing implications. All said, sustainable agriculture practices, policies and finance can effortlessly move agriculture sector onto the resilient pathways, paving way for the food security, poverty eradication and mitigation of climate change. Thank you. Thank you very much.